everyone, welcome to the Learner's House. In this video, we will start central limit theorem in R. So I hope before starting this video, you already know the concepts of central limit theorem in theory. Either you have watched my video or you know by yourself. That would work too. So if you don't, I would suggest that you should watch the theory video first. So in this video, we will proceed with a question. We will do one question on central limit theorem, and that question is made up in a way that it will cover almost all the concepts of central limit theorem. So if you are struggling with that, then please watch this video till end. I hope all your doubts will get cleared. So first of all, the question says that let x be the amount of time in minutes a postal clerk spends with his or her customer. This time is known to have an exponential distribution with mean 4 minutes. First part में बोला है using seed 50 simulate a sample of size 100 from this distribution. I don't think इसमें कोई problem होनी चाहिए. This we can do pretty easily. So सबसे पहले x क्या है? Amount of time a postal clerk spends, and now we know that our x follows exponential distribution with parameter 1 by 4, because the 4 is the mean here, which we can check. Yes, so it is mean 4 minutes. Alright, next let's do the first part. This information is clearly optional to just clear the concept. Now let's set the parameter L, which says lambda 1 by 4, so that we don't have to write 1 by 4 again and again. And then set.seed is the command we have to write. I hope till now you all know these few things. Like the things which I have already explained in my previous video, I won't explain those in this video or in the coming videos, because that is just time waste, and those who are studying with the videos regularly, it wastes their time and my time also. So please make sure that you know the basic concepts. Either way, you cannot do otherwise. Alright, so now we have to generate a sample. So let's save the sample into a vector E. This is the sign of saving. Now we will write REXP because this follows exponential distribution. Now how many values we want? So we want 100 values. So we will write 100 here, comma lambda. And now let's run it quickly. So here we can see that we have a vector E which contains numeric from 1 to 100, and these all are the values. If we want, we can check the head also. Like from head you can match your answers with mine. Now we have to do a second part. Obtain the histogram of the simulated data. This is pretty easy. We just have to create the histogram. So let's do that. Part 2 it is. We will write HIST, hist. Now we want histogram of E, so we will write E here, comma. Now we can write X labeled. So what is X labeled here? This is time a postal clerk, let's just write clerk, spent. If you want, you can extend this also. Now we will give y-axis, we will give labels to the y-axis, which is, if you want frequency, you can calculate, draw that way also. Otherwise we can take probabilities too. So now we can write frequency here, main plot of a data plot of our data on time our clerk spends, we can write histogram instead of this. Otherwise, you can write your other main heading also. This can differ. Now we have our histogram here. If you want, you can apply breaks too. This was it for this part. Let's check the other part. Third part. Part A says create a vector S which contains 1500 zeros. Alright, so we want 1500 zeros only here. Let's do this. This is part 3. Vector S. We want 1500 zeros, so we would write 1500, comma 0. Now, the B part of third says using for loop, store the sum of the results. For loop, we have to use for loop. First of all, it is clear here. Store the sum of the results obtained in the ith sample of 100 simulations in the ith element of S. So what we have to do, this is a bit complicated language, but we can understand this bit by bit. This says store the sum of the results. We have to store the sum of the result obtained in the ith sample of 100 simulations. We have done the 100 simulations in our part 1. We have to determine the sum of that, and then we have to store that in the ith element of S by using seed 60. So what we will do, we have created a blank vector first of all, then now we will set the seed, set dot seed 60 it is, and then we will write for I in 1 colon. Now you have to think that what should be here. We have to save, like we have to do the simulations and save that into ith element of S, and S contains 1500 zeros. So that clearly means that we have to do the run the loop 1500 times, because we have to save 1500 values. And how we will save 1500 values? By running the loop 1500 times. Now what we will do here, we will write E 100, comma L. What it will give us? It will take lambda as L, which we have saved earlier, and give us the simulations from. So we have done this from the exponential distribution. This is saved in E. Now after this, what we have to do? We have to take the sum of this E. We have to take the sum of this E and save it into the vector which was S and ith value here. I will explain this once more once I complete the code, because I believe that it's easy to explain and to understand too once it gets completed. Alright, so now we can think, we can see here that what is going on. We have like written this command for loop. Now the first time the loop runs, the value I equal to 1 will get saved, and then as we go down, like in this step, what will get done here? Now we will see that E is the vector which is like storing 100 values from exponential distribution in it, and then we are taking the sum of those 100 values and giving that to the first value of S. Similarly, the second time the loop runs, E will generate more 100 values and this will calculate the sum, and then that will get saved into the second value of S. Similarly, E will get he will give us more 100 values, like other 100 values, and then determine the sum, and then that will get saved into the third value of S. So this is the way that how the loop will work here. Now we can read the question once more to let us know that we have done everything right. So this says that using for loop, store the sum of the results obtained in the ith sample of 100 simulations. Like the 100 simulations we have, determine the sum and then save that into the ith element of S. So first sum will get saved into the first value of S, second sum will get saved into the second value of S. So this was the easiest explanation of loop. However, I understand that this could be a bit tough for you all, but by practicing each day, you will master the concept. So I hope this is clear now. Now let's just run it. Now we can see that our S vector contains few values except blank. So this was it for this question, and now we will do fourth part. Now we will start part 4, which says that draw a labeled histogram of the probabilities of the results in S. If you didn't have note down these questions, then please take a screenshot or whatever, so that you will know the reference that which question we are doing. So this is part 4, and it says draw a labeled histogram of the probabilities of the results in S. So we have to make a histogram of S. So we will write command hist S, comma, we have to plot the histogram of the probabilities. So what we have to do here, we have to write prob equals to true, so that the R knows that we are plotting the histogram of probabilities. Now we can write X label like that. This you all can write. So I am leaving this on you. Now let's run this. So it looks like this. Now second B part of part 4 we have to do. This says that superimpose on the histogram a graph of approximate PDF of the sums using CLT. So on this histogram we have to superimpose a PDF. We have to superimpose a graph of approximate PDF of the sums using CLT. So just a quick revision, you all know that in CLT what we do, we say that the sum and the mean, like the X bar and the summation Xi, follows normal. So we can write it like this, that our sum will approximately follows. Let's add a quick comment here. Our sum follows normal with mean n mu and variance n sigma square. So we will write it this way. Now we know that our mean means mu is like the data follows exponential with mean 4. So our mu is 4. So here the mean would be 400 because we have the 100 values. Now our sigma would also be 4. So now we would write here variance equals to 1600. Now what we are going to do here, let's plot the histogram alright. So we have already plotted this histogram here. We have to superimpose the line on this. So this is a pretty new thing, but we will understand this the very easy way. So stay concentrated. We will write here command curve. Now this command curve, the inputs would be denorm, because from CLT the sum follows normal. Now the parameters, which are first of all we will write x, comma 400, this is the mean, comma standard deviation. You all should know by now that the denorm commands or all the commands of norm contains standard deviation and not variance. So we will do the square root of 1600 here. Now our this work is done, but the command isn't completed yet. The bracket is ending here. We will write after denorm, we will write comma. Line width, if we want to give, we can give it to, we can give it a color red. Now there is something which is still pending, this x. What is this x? If you look in this environment, there is no vector as x. So first of all, we want to state that what our x is. Otherwise, if we will run this, then there would be an error. So let's define our x. First of all, we have to check the range of s, that from what number to what the s is. So we can see that s is lying here from 274 to 542. So our x would also lie in this range. Obviously, this x cannot be outside of the range because we want to superimpose this on this histogram also. So we will write here x arrow. We will generate a sequence 250, comma, this could be, let's say, 600 for the safer side. And since this is the continuous distribution, we can take by equals to 0.1. Now let's run x, and now this curve. So this curve is pretty different. We can see that it hasn't superimposed on our histogram. So what mistake we have done is, we have to write a thing which is add equals to true. We will see that what this add means here. Let's run a histogram before this. Now let's run this. So now we can see that it has superimposed this. So what add is, let's write it in help box for the better understanding. We will write curve here. See, the curve means curve and then expr, which is the name of a function, from where to where we want, and then add is false. By default the add is false. So what this add is, now we can see that this add is if we want to add this curve on the existing plot or we don't. So we can see if true, or add to an already existing plot. If we will let me zoom it out. So if we will put add equals to true, then what this will do is, the curve will get added to the already existing plot. So this is the mistake which we did earlier, because by default the add is false. At any point of time or at any command, if you get stuck, then write it in help box. This is even allowed in the IFOA examinations. So we can do that. After this, I guess that finishes our part. So yes, now we will come to our part 5th, which says find the probability that the sum of time spent with 100 customers is greater than 400 minutes. Sum of time spent. We have to calculate the probability of S. Keep this in mind. We have to calculate the probability of S because this is asking for the probability of the sum of time spent with 100 customers is greater than 400 minutes. Alright, so the sum of 100 customers, which is saved in S. So this is greater than 400 minutes. We have to calculate this is from empirically using our simulated data. This is our part 5th. First we will do it empirically. So how we will do that? Let's see. We have to determine the probability of S, and the condition which we put always in square brackets. The condition is that S should be greater than 400. Alright. Now what this will do? This will give us those numbers which are greater than 400 in S. But we don't want this, we want the length. Now let's see the count. So these are 733, you can see here. This is not visible, let me do it again. So the length is 733. Now we don't want this too, we want the probability. So we will divide it by the total count of S. Now we can see that this is 0.488667. Now this was it. Then we have to calculate the same probability theoretically using CLT. So by CLT we know that this sum follows normal distribution. So we will calculate the probability with the norm command. But think, do we need to use dnorm, pnorm or what? So dnorm will not work here because we have to calculate the probability of an interval. So we will write down pnorm. We want probability of greater than 400. So we will write 400 here, comma, the mean is 400 and the standard deviation is 40. But we want the probability of greater than 400 and not till 400. So we have to write an additional argument which is lower equals to false. So let's run it quickly. This is 0.5. We can see that these two probabilities are bit close, which says that the data, the S is approximately following normal distribution. Now in part 6th it says repeat parts 4th and 5th for sample sizes of 10, 30, 50 and 200 customers. All 4 histograms should be displayed simultaneously. So first of all, let's repeat part 4th for these all sample sizes. Part 4th says draw a labeled histogram of the probabilities of the results in S. So we have to make a histogram again, but by changing the sample size. Now we don't have the sample size of 100, we have the 4 different sample sizes. So let's do it. First of all, there is a command. In bracket, in the question, it is written that all graphs should be displayed simultaneously. So what we have to do for that, this is the command. This will split the plot area into 4 parts and our graph will be displayed simultaneously. So let's write C2, 2, which 2, 2 means 2 parts. 2 parts above, 2 parts below. So this will overall give us 4 total parts. We can run this right now or when we will run the graph. So now we want, so we have the different sample sizes. So let's run X and then we will generate that. Let's remove this X from here as of now, otherwise you all will get confused. So let's understand that what we have to do. We have the changed N now and we have to determine the histogram again. So how we will make histogram again? For histogram we need this E. We need this E. Now for this E we have to do this because sum is this S command. So we have to repeat all over this again. So let's just do that. This is part 6 itself. So first of all we will save our N, which is 10 here. I am writing the first case with N equals to 10 and for all the other N I'll just copy paste. So first of all we will make a blank vector 0, 1000. Let's make 1000 zeros, but let me the question says that repeat parts 4th and 5th, and in all those parts we had S which contained 1500 zeros. So here also we will generate 1500 zeros. And after this S, what we have to do, let's set seed which is 50 here. And now we will write the for loop command. For I in one column 1500, we have to run the loop 1500 times. Now we will generate vector E from REXP. 100 values, not 100, 10 values, because n is now 10, which was earlier 100, comma L. Now we want to save the sum of E into the ith value of S. This will make our proper S vector. Let's run this whole part. After this, we can write histogram S, comma, probability equals to true, and let's just leave the headings as of now. Now we want to superimpose. So first of all, let's make a histogram. So now you can see that this is only at the 1/4 part of the total area, because we have used this command already. Now we will superimpose by CLT here lines x comma d norm x comma 400 comma 40. Let's just write color equals to red. Now this will ask that what our x here is. So we can take this x like the way we did earlier. So we can save our x. We can write it like sequence. Before that, let's find out the range of S. So this is 10 to 96. Let me clear it and show it to you all. So we can, for safer side, write here from 0 to 1000. And since this is continuous, we can write by equals to 0.1. So this will give our x here. Now we can run this command. But this is not clear here. Let's remove this and do this again. I guess there is some error. Yes, we haven't written type here, that what type of curve we want. So we want L, which states that we want line. But this is on the whole part. S is here. Let's run this command again. Type is fine, but this is again showing the line here. Let's see what the problem is. This is taking density. This is also fine here. There is a mistake. We have used this mean and variance according to n equals to 100. But now n equals to 10. So the mean would be 40 and the variance would be, yes, that would be 42. So we have to take square root of 40 here. Now let's check if it works now. Let me just clear this. Yes, so now this is working fine, although you can see that the graph is not complete here. So for this, what we can do, we can increase the y limit. After increasing the y limit, we can get the proper graph. Alright, now you all can do this for all the other three n. Now I am proceeding to the next part, part C. 7th, I guess it is. So part 7th says, find the mean and variance of your simulated sample. Like before going further, I want to discuss the result which will come in this part. After, whenever you will increase the size of n, please note the shape of this graph, and the coordination of this graph with our histogram. So what we will see is, as we are increasing n, the superimposed line is same as the histogram. Like the fit would get better with each increase in n, because of the fact that as larger our n is, the normal approximation holds. So we can do that also. Next, part 7th, find the mean and variance of your simulated sample and compare it with the theoretical mean and variance. So let's calculate the mean and variance of simulated sample. Our simulated sample was stored in S earlier. So let me run the previous part again, so that we will have an original S, because now we have an S according to n equals to 10. So we have to do this thing again. Now it is fine. So we can write here mean S, variance of S, and according to CLT, if we see, then the mean would be n, which is 100, original n, into the mean is 4, like the exponential mean is 4. So we can write here original mean is 4. Yes, this is fine, 400. And then the variance would be which we have done 1600. This would be 160 and not 40, because the L part would get squared up. Now this would be 1600. So let's compare it with the empirical one. Here our mean is 401, and in that case that is 400 with CLT. And the other part, that is 1698 variance, but our original variance, like not original, the approximate from CLT is 1600. Now we have to do the next part. Calculate the median, lower and upper quartiles empirically and theoretically using CLT. We have to determine median, lower and upper quartiles. So let's calculate this. So you all know that for quartiles we have the command quartile when we have to calculate this empirically, and theoretically we can do this, like we have to calculate IQR, which we will get by Q3 minus Q1. Alright, where Q3 is the upper quartile and Q1 is the lower quartile. So I hope that this you all can do, and also the one part should be the homework also. So I hope the CLT is clear for all of you. This could be a bit difficult, but if you give this video a good amount of time and understand all the concept and do all the questions, then I guess that this wouldn't be tougher at all for you. So thank you so much for watching. Keep watching, keep learning. If you have learned something from this video, then please hit the like button, write down the whatever you want to say in the comment box, and use the share button. Thank you so much.